You've probably heard the term machine learning thrown around all the time, but what does it actually mean for a machine to learn? In this explainer, we're going to pull back the curtain on these things called neural networks to see exactly how they go from knowing basically nothing to recognizing incredibly complex patterns. Let's dive right in.
All right, so take a look at this. Even though it's messy, it's kind of low res, your brain instantly knows what it is. It's a 3. We do this kind of thing without even thinking about it, right? We can recognize all sorts of handwriting in a fraction of a second. But how would a computer see this?
For a computer, this is actually incredibly difficult. I mean, think about it. You can't just write a bunch of if-then rules to identify a 3. What about all the different ways people write? The different angles, the loops, the slants? It would be an impossible list of rules to program by hand. And that is exactly why we need a totally different approach. We need machines that can learn from examples, a lot like we do.
So how do we even begin to teach a machine how to solve this kind of visual puzzle? Well, to understand the complex stuff, we're going to start with something much simpler and build our way up from the absolute basics, one piece at a time.
Okay, let's forget about handwriting for a minute. Imagine a much simpler job. We want to predict a house's price based on just one single thing, its size in square feet. This super simple model is going to be our stand-in for a single neuron, which is the basic building block of any neural network. So here's the data we're going to work with. We've got a few examples of houses, and there's a pretty clear relationship here, right? As the area goes up, the price generally goes up. Our goal is to create a model that can learn this exact relationship.
So our first, most basic model, our little baby neuron, works like this. It's super simple. You take the input, which is the house size, you multiply it by a special number that we're going to call a weight, and whatever comes out, that's our predicted price. That's it.
Okay, so what is this weight? The easiest way to think about it is like a volume knob. It controls how much influence the input, the house size, has on the final output. If the weight is big, the size has a big impact on the price. If it's small, not so much. And the whole game here, the entire goal of learning, is to find the absolute perfect setting for this knob.
But, there's a problem with this simple setup. A model that only has a weight is forced to have its prediction line go right through 0. That means a house with 0 square feet must cost $0. If you look at our data, that limitation means our line just can't fit the real-world examples very well.
So to fix this, we need to add a second knob we can turn, and we call this one a bias. A bias is just another number that we add to the result. It's like a starting point. It lets us shift the whole line up or down. This gives our model way more flexibility, and now it can find a much better fit for the data.
Okay, so now our model has 2 knobs to turn, a weight and a bias. But how does the machine figure out the best settings for them all by itself? This, right here, is the absolute heart of machine learning.
Well, first things first, before the machine can get any better, it has to have a way to measure how wrong it is right now. And that's where something called a loss function comes in. It's basically just a formula that calculates a single score, a number that represents how far off the model's predictions are. The goal is simple. Get that number as low as you possibly can.
Let's make this real for a second. Look at that 1,600 square foot house. The actual price is almost $330,000, but let's say our model's current guess is $288,000. That's an error of about $42,000. The loss function takes that error, squares it to make sure it's a positive number, and then it does this for all our other examples and averages them together to get one final score that tells us how wrong the model is overall.
So this whole process we just described, taking the inputs, running them through our model with its current weights and biases, and spitting out a prediction, that whole thing has a name. It's called the forward pass. It's step 1. The network just makes its best guess.
All right, so the machine made its guess, and we've calculated the error score. We know how wrong we are. The goal now, as Matt Mazur puts it so well, is to adjust our knobs, those weights and biases, to make that error smaller. But which way do we turn them, and by how much?
The answer is this absolutely brilliant algorithm called backpropagation. You can think of it as the backward pass. After seeing the final error score, the network literally works backward through itself. It uses a bit of calculus to figure out exactly how much blame each individual weight and bias has for the total error. Then it knows precisely which knobs to turn and which direction to turn them to get a better result next time.
Okay, let's take a breath. We have the fundamental pieces now. A forward pass to make a guess, a loss function to measure how bad that guess was, and backpropagation to learn from the mistake.
Now we can finally scale this idea up from our simple house price predictor to that much harder problem we started with, recognizing handwritten numbers.
So instead of one neuron, we now have layers of them. The input layer has 784 neurons, one for every single pixel in the image. The final output layer has 10 neurons, one for each digit from 0 to 9. And in between are these hidden layers where the real magic happens. The neurons in these layers learn to spot simpler patterns on their own, things like little edges, curves, and loops.
But hold on a second. There's a big piece of the puzzle missing. Everything we've built so far, multiplying by a weight, adding a bias, that's all just linear math. It just makes straight lines. So how on earth can a network built from straight lines learn to recognize something with complex curves, like a handwritten digit?
The secret ingredient, the real game changer, is something called an activation function. It's a tiny bit of nonlinear math that we apply to the output of every single neuron. Its only job is to break the straight line, to introduce a bend or a curve into the system. This is what gives the network its power.
And this right here is one of the most popular activation functions, called ReLU. It's incredibly simple. All it does is look at a neuron's output. If the number is negative, it changes it to 0. If it's positive, it leaves it alone. That tiny little kink at 0 is the nonlinearity. And when you stack thousands of these simple bends on top of each other, layer after layer, the network can suddenly learn to create and recognize almost any complex shape imaginable.
Now, the network we've been describing is a pretty standard feed-forward network, but it's really just the beginning. Think of it as just one member of a whole family of neural networks where each one is a specialized tool designed for a different kind of job.
The one we built, the classic ANN, is great for structured data, stuff you'd find in a spreadsheet. But if you're working with images, you'd use a CNN, a convolutional neural network, because it's built to understand spatial patterns. And for things that happen in a sequence, like words in a sentence or audio, you'd use an RNN, a recurrent neural network, because it has a kind of memory.
So when this is all said and done, what's the big takeaway? When you hear that our neural network learns, it isn't magic. It's a very clever, automated mathematical process. It's all about making a guess, measuring how wrong that guess was, and then using backpropagation to systematically tweak thousands or even billions of tiny little knobs until that error is as close to 0 as possible.
And this leaves us with a really fascinating, kind of mind-bending final thought. If this incredible ability we call learning is, at its core, just a mathematical process of minimizing an error score, what does that imply about intelligence itself? And what does it really mean for a machine, or maybe even for us, to truly understand anything at all?